Hi everyone, I'm Hyungkyung Lee from KAIST. The paper I'm presenting is Unconditional Image Text Pair Generation with Multimodal Cross Quantizer. This is a joint work with my colleagues Seongjin Park, Junseok Lee, and Edward Choi. Our work is about image text pair generation. The deep generative model is an active research area, but they mainly focus on a unimodal generation, either unconditional or conditional. Unconditional generation generates image or text from scratch. Conditional generation generates image or text conditioned to text or image. Yet, unconditional multimodal generation has not been much explored, so we extend those works to unconditional image text pair generation. We generate image text pairs simultaneously without any conditional input. The contributions of our paper can be summarized as follows. The first one is unconditional image text pair generation. For the first time, we propose a novel vector quantization method that learns the quantized joint representation space for unconditional image text pair generation. And the second one is semantic consistency of the generated samples. Our experimental leader revealed that our model generates a semantically consistent image text pair on multiple benchmark datasets against several baselines. The last one is multimodal semantic correlation. Our model learned the meaningful semantic correlation between image and text in the quantized joint space. And also, it turns out that the quantized joint space leads to semantically consistent image-text pair generation. This is our method. We adopt a two-stage approach. In first stage, we construct our model based on a VQVA. Our model takes a masked image text pair as input and learns a quantized joint representation space. Then the input is converted to a unified code sequence. And next, in stage 2, autoregressive transformer model a joint distribution over the code sequence. And at inference, our model decodes the sampled code sequence to an image text pair. We evaluate our model on one synthetic text-augmented MNIST called Caption MNIST and 3 public benchmarks, including Oxford Flower, Cup, and Cocoa. This figure shows the example of Caption MNIST. Each pair contains several color, digit, and position. According to the field quadrant, we refer to each subset as single and code 1 to code 4. And this is the example of Oxford Flower, Cup, and Cocoa. Additionally, to study the effect of the quantized joint space for generating semantically consistent image text pair, we construct a corrupted dataset called degree dataset. We gradually adjust the degree of alignment between image and text. For caption MNIST, we replace the color and digit in the caption with other random colors and digit. And for flower and cup, we randomly replace the color with other colors. We first studied the effect of our model in constructing multimodal semantic correlation in the quantized joint space. This results show that our model can identify the correlation and the difference between image and text. Also, we can observe that the transformer encoder for cross-modal attention and the text compression are essential for the multimodal semantic correlation, and also the input masking plays a significant role. We also visualize the attention map of the transformer encoder. The deeper color indicates a higher attention score. Although we do not provide any explicit guidance, our model can properly attend to the related tokens that correspond to the image patch. This figure shows the t-SNE visualization of the unified code sequence with our model and 1.0 baseline for 10 digits per color on caption MNIST single pairs. Figure A and B show that our model has a unique cluster for each digit while the baseline has 2. Because there are 2 types of text in the single pair. The first one is this digit is color, and the second one is this is color digit. As shown in figure C and D, our model can capture the correlation between them, but the baseline completely fails when even though they contain the same contents. This table shows the semantic consistency of the generated image text pair. We can see that our model outperformed all baseline on every quadrant on caption and list. Also, on flower and cup, compared to the baselines, our model performed well in all metrics, and it indicates its capability to generate semantically consistent image text pair for real-world dataset as well as carefully controlled synthetic data. This figure shows the comparison of the generated image text pair on caption and list. We can see that our model can generate semantically consistent image text pair and also show high fidelity image and text. In contrast, the baselines show its poor ability to capture the relationship between image and text. Similarly, our model shows its superiority on flower and cup. Unlike our model, the generated images of the baseline are incomplete and also cannot generate detailed part, and they generate overlapping words. In summary, in this paper, we present a novel vector quantizer that learns a quantized joint representation space for unconditional image text pair generation. The experimental results demonstrate that the quantized joint space with the multimodal semantic correlation increased the generation of semantically consistent image text pair. And our approach shows its superiority in these two aspects over several baselines. One promising application of our approach is training conditional generative model with 3 or more modalities. By considering our model as a multimodal tokenizer, the generative models can generate other modalities given a multimodal code sequence or vice versa, which remain as future work. And this is the last page of the presentation. Thank you for the listening.